Many of you may have heard about neutrinos before. So would you like to just share what you know about a neutrino?
They're like the chargeless, nearly massless version of particles. Like they have the same flavor. They have no charge. They're massless, and they interact very little with things, so they can pass through concrete and iron, no problem.
Okay. Anybody else who wants?
Yeah, similar to what Akino said, there's probably thousands of them passing through all of us right now, but they rarely ever interact with anything.
Okay. So thousands. You think that is too much or too little?
That's too little, actually. That's a very conservative estimate.
Fairly conservative estimate. So how did you get this 1,000 from?
Because I once read in a book, I don't remember what was the unit area, but they're basically given some unit area through which you get 1,000 neutrinos per second. It was a small area. I don't remember exactly how large.
Okay, so today we will try to see if you put your thumb to the sun, we'll try and estimate how many neutrinos are passing through it every second. Okay, let's first get a glimpse of how neutrinos came about. Okay, how did we know of the existence of a neutrino and how was it first discovered? So neutrino was actually something which was theoretically predicted by Wolfgang Pauli in 1930. So his prediction was based on the problems of energy conservation during beta decay. The two forms of beta decay, which is neutron to a proton plus an electron plus an antineutrino. And antineutrinos are usually denoted by a bar over here. But I think I was not savvy enough with PowerPoint to be able to do that. So I've just written anti in front. Sorry about that. And beta decay plus, where a proton in a nucleus can decay into a neutron plus a positron plus a neutrino. And what happened was there was a whole range of energies which the electrons had during beta decay. And Pauli was trying to find a solution to it. And the way he could solve it was to say that there has to be a particle of very little mass, nearly very low or nearly zero mass. And it also had to be neutral, okay? Because these equations had to conserve charge. And he was actually not very confident of the results. And I think it was a few days before a meeting in Tübingen in Germany that he wrote this letter in German. He says, the English translation would be, "Dear radioactive ladies and gentlemen." And he talked about his idea. That was in 1930. And this little bit of history over here, which I think the CERN, which is put together. This is from a collection of letters which Wolfgang Pauli had written. And this was retrieved later from one of the participants of the meeting, the well-known physicist Lise Meitner. And that was what Fermi's prediction was. And the term neutrino was popularized by Enrico Fermi, which in Italian would mean the neutral, the little neutral one. And how was it discovered? How was it actually first discovered? And it was discovered in 1956 by Frederick Rhines and Clyde Cowan. What they tried to do was to see whether there could be a copious source of neutrinos and to try and detect it by its interaction with matter. So this was what they did was they initially tried it somewhere else, but later they went to a reactor plant, Savannah River plant near South Carolina. And using neutrinos, they sort of thought of two reactions, that there would be a copious source of neutrinos. And one of the reactions would have been an antineutrino reacting with a proton to produce a neutron plus a positron. And if this happens, then the positron and the electron would annihilate to produce gamma rays. But Rhines and Cowan thought that that would not be a foolproof, a firm proof of it. So the other reaction they want to look for was neutrons. They set up a tank with cadmium chloride, and the neutrons would react with cadmium 108 to produce an isotope of cadmium, which should be at a higher energy state, and that would decay, emitting a gamma ray photon. So you had actually two sources of gamma rays, and the way they set up the experiment was that the one from the cadmium excitation would come a little later than the electron-positron annihilation. A delay very small, but just 5 microseconds or so. And they could show by detecting the gamma rays with the help of these detectors over here, photomultiplier tubes, which would detect these gamma ray photons, that there was indeed the evidence for a neutrino. So this was the first experimental evidence to show that a neutrino, which is predicted by Wolfgang Pauli, did exist. And they rushed off this telegram to Wolfgang Pauli in 1956. In the basic properties of the neutrino, they come in what are called 3 different flavors. There's the electron neutrino, the muon neutrino, and the tau neutrino. Don't worry about the whole graph over here. We're not going to discuss the whole model of elementary particle physics, but we just focus on the neutrinos. And it is important to note that there are 3 different types or 3 different flavors, that it is called, of neutrinos. And they're associated with interactions with the electron, the muon, and the tau particle, tau. And there are antiparticles for each of these particles. These set of particles are collectively referred to as leptons. And this Z boson and W boson come into play during the interactions, but we'll not worry about that in this lecture at all. So basically, the important thing to remember is that neutrinos have very little mass, they have no charge, and they are what are called spin-half particles, which refers to the angular momentum of the particle. Is a quantum mechanical concept, and that is also half for each of these particles. This is the electron, muon, and the tau particle, also spin-half particles. Okay, as you know, these particles also have their antiparticles. So there's an antiparticle for each lepton. Now, Bruno Pontecorvo hypothesized in, this was in 1957, that neutrinos may oscillate. Okay, oscillate means that one type of neutrino may change into another type of neutrino while it is in transit. An electron neutrino may become a muon neutrino may become a tau neutrino. So this was hypothesized in 1957. He also predicted that neutrinos may originate from supernovae, which are, as you know, the explosion of massive stars. Stars far more massive than our sun. 3 types of neutrinos we just mentioned: electrons, mu mesons, tau mesons are associated with it. And we note the mass to be very small. And how small is it? And that is one of the experiments which has been set up and is still running, is the Karlsruhe tritium neutrino experiment, where they monitor the decay of tritium, which is a heavy isotope of hydrogen, where a neutron decays into a proton, an electron, and a neutrino. So they estimate the energies of the decaying products and attribute the rest of the mass to the neutrino. So they got an upper limit of 1.1 electron volts. I think there's slightly better numbers available now. This is from their first trial run in September 2019. But basic message is that they have to have mass, because without mass, the changing of flavors will not take place. If changing of flavors takes place, it has to have mass, but the mass has to be very small, which is, the limit is over here is 1.1 electron volts. So no charge means it is not affected by electric and magnetic fields. Okay, not affected by electric and magnetic fields, which means that if it comes from a particular source towards you, it should come straight towards you. And unlike the cosmic ray particles, which are charged particles, can get deflected by the magnetic field or irregularities in the interstellar medium, neutrinos, if they're generated, will come straight towards you. They will not be affected by the electric and magnetic fields. And as Aquino mentioned, the cross-section of interaction is very low. I put some numbers over here. It's about 10 to the power of, for a 1 GeV neutrino, again, it's a bit energy dependent, is about 10 to the power of minus 38 centimeters squared. Whereas for an electron or a proton scattering in a plasma of about 10 to the power of 4 Kelvin, you can see it is small, it's 10 to the power of minus 15 centimeters squared, but it is orders and orders of magnitude. It's 23 orders of magnitude larger than the cross-section interaction of a neutrino. So neutrinos can traverse great distances without being absorbed. It can go right through the Earth. It can go right through us, let alone right through us. It can go right through the Earth. So neutrino detectors are built deep underground. Unlike optical telescopes or millimeter wave telescopes, which you put them on mountain tops to minimize the effects of the atmosphere. But you can see over here that when you want to detect neutrinos, you have to go deep underground. You want to deep underground also because you want to eliminate other sources of noise which might affect the signal. And you need a large target mass. Large target mass, why? Because you want to maximize the possibility of interaction. Most neutrinos would just go through, but there would be some who would interact, and you want to just catch hold of those. Because they have so little cross-section of interaction, they give us a glimpse of the interior of stars. Today, we have detected neutrinos from the sun, but without the neutrinos, we would not have been able to get a glimpse of the interiors. Now, today we know that the number of neutrinos, as we shall see, is consistent with the standard solar model of how energy is generated in the interior of the sun. Supernova explosions also generate a huge amount of energy. And this also enables us to test whether our models of supernova explosions is correct or not. Neutrinos also carry information about the very early stages of the universe, but we have not been able to detect these neutrinos so far. So first, let us just see what are the possible sources of this extremely low mass, no charge, spin-half particle categorized as leptons. So one, as I mentioned, is from the cosmic neutrino background. Just as we have the cosmic microwave background, this would relate to the very early phase of the evolution of the universe. As we understand it today, or as we theorize today, that in the first few nanoseconds, which we do not have a handle on, that the universe consisted of fundamental particles like quarks, which go to make up protons and neutrons, leptons, neutrinos, and their antiparticles, gluons, photons, and then later the quarks combine to form neutrons and protons. Then when you go to the millisecond to second sort of stage, you have neutrons, protons, electrons, positrons, neutrinos, antineutrinos, and photons. Then as temperatures begin to fall in about a second or so, that the neutrinos decoupled, and we should really have a sea of neutrinos today at a temperature of about 2 degrees Kelvin. But so far that has not been detected. And as we go to longer time scales, you'll initially form neutrons will combine with protons to form light nuclei, hydrogen and helium, which are the most abundant. And after about 300,000 years or so, the universe cools, atoms form, hydrogen combined with electrons to form stable elements. The universe becomes transparent to electromagnetic radiation, and we have the cosmic microwave background radiation, which was discovered by Penzias and Wilson, for which they got a Nobel Prize as well. We talked about the cosmic microwave background radiation when we talked about the radio universe. But today we will just consider, neutrinos. So there is a sea of cosmic neutrino background, which we have not detected, but if our theory is correct, if our understanding of the universe is correct, that should exist. Besides the neutrino background from the very early phase, when the light elements were synthesized and there was neutrons, could decay to protons plus electrons plus antineutrinos, and you can get isotope of hydrogen becoming 3 helium through that process, electrons and antineutrino decay of neutron within the nucleus into a proton could happen within the first few minutes of the Big Bang. And you can see that this would also generate neutrinos over here. This is what is referred to over here as the Big Bang nucleosynthesis. This is the 3 helium component. This is the neutron decay component. But these are again components we don't have any observational sort of handle on it. Then there are solar thermal neutrinos, that the processes which are going on the surface of the sun, where high energy photons could scatter off electrons to generate neutrinos, antineutrino pairs. And these are what are referred to as solar thermal neutrinos. And these are very different from the solar nuclear neutrinos, which are generated by nuclear reactions going on in the center of the sun, or the central region of the sun. And you can also see that the energy levels are slightly different, that these are more energetic, these are less energetic. And you can see the cosmic neutrino background is only about 10 to the power of -3 to -6 electron volts or so. So extremely low energies. But as you go to higher energies, we come to first the solar nuclear neutrinos which are generated. And of course, our nuclear reactors generate a lot of neutrinos, which is marked over there. Then we also have atmospheric neutrinos. So atmospheric neutrinos and also geoneutrinos. Geoneutrinos which get generated due to naturally occurring radioactive elements on the surface of the earth, which decay, giving rise to neutrinos. Then you have the diffuse neutrino background as well. And this diffuse neutrino background, we shall see a bit more, perhaps a little later, they carry almost all the energy during a core collapse supernova. What is a core collapse supernova? These are when the massive stars collapse to form these core collapse supernovae, and releasing about 10 to the power of 53 ergs in energy. And of these 10 to the power of 53 ergs in energy, almost 99% of it gets carried away by neutrinos. So, and these neutrinos would be traveling all over all over our galaxy, all over everywhere. So this gives rise to the diffuse neutrino, supernova neutrino background. Neutrinos would be, this supernovae would go off not only in our galaxy, but in other galaxies as well. So a diffuse supernova background would permeate space and give rise to what is a neutrino background. So we haven't detected that either. So atmospheric neutrinos, these are due to produced in the Earth's atmosphere by interaction with cosmic rays, as we just saw a little while earlier. And then cosmogenic is what I mean by cosmic rays, which are also generated, neutrinos which are also generated by interaction with cosmic rays, but it could happen near the source of the cosmic ray particles rather than being generated in our atmosphere. Have a wide range of possible sources, and this comes from our theoretical understanding of physical processes that go physical processes that go in our universe, and we need to, but we have not detected most of them. Okay? What we have detected, we will sort of discuss in a very short while, but you can also see in this graph that the energy range which neutrinos also cover from our understanding is many, many orders of magnitude, about 10 to the power of 24 orders of magnitude. So that's a huge range as well. Now, let's look at the neutrinos which have been detected. We'll not discuss too much of atmospheric neutrinos. A little bit we mentioned while talking about cosmic rays, but let us discuss one of the very important sources of neutrinos, which is the sun. And detection of neutrinos from the sun was extremely important to validate our understanding of energy generation in the sun itself via what is known as the standard solar model. As you know, the bulk of the energy is generated by what is called the proton-proton chain. And I've just written down the nuclear reactions over here. Initially, two protons to combine to form a deuteron, along with a positron and an electron neutrino. Then the deuteron combines to form a proton, with a proton to form a helium nucleus and a gamma ray photon, and a photon. Two of these helium nuclei will combine to form a helium nucleus and also releasing two protons in the process. And the reaction is exothermic, which means it releases energy, which is 26.73 MeV, million electron volts. So what you're effectively having is 4 protons, which are combining to form a helium nucleus, releasing in the process both positrons as well as electron neutrinos, and releasing 26.73 MeV of energy per reaction. So now we can try and work backwards, because we know what the solar luminosity is, This gives you the reaction for a single chain over here. So do any of you remember how much the solar luminosity is? Okay, it's good to remember these numbers. It's roughly about 4 into 10 to the power of 26 watts, or you can multiply by 10 to the power of 7 to get it into ergs per second. Okay. And on the 3 reactions which I just mentioned, the proton-proton reaction is the slowest. This has to do with the nuclear physics of what is going on. And that is why our sun keeps burning slowly, because the rate at which these reactions take place also determines how long our sun is going to last. This is faster, and the strong nuclear reaction is again slow, but not as slow as the weak nuclear reaction taking place in the first one. Now, 4 protons are required to produce a helium nucleus, and 26.73 MeV is released. So 1 MeV I've written down over here is about 1.6 into 10 to the power of minus 13 joules. So knowing what the solar luminosity is and the number of protons which are required to produce that, I can try and calculate what is the number of protons which are released per second, okay? Because this is the number of ergs per second that is released. 4 protons, I multiplied this by the luminosity, and per release of energy, 26, I've converted this to joules over here to get everything into the same units. Then I will get about 4 into 38 protons are being used, okay? It's a huge number, isn't it? It's a huge number. So, but you can, and you might be getting worried as to if there are so many, protons which are being used up every second, how long will our sun last? Isn't it? So you can do yourself a little sum, and you know the mass of the sun, which is about 2 into 10 to the power of 30 kilograms, right? 2 into 30 kilograms, and you divided that by a mass of a proton. So, I mean, what I'm doing is not exactly correct, because not all the mass of the sun is hydrogen. There is also helium and trace elements. But if I just, for simplicity, just to show you that you need not worry that the sun will soon get rid of its hydrogen, see this huge number. If you divide the mass of the sun, which is 2 into 10 to the power of 30 kilograms, by the mass of a proton, which is about 1.7 into 10 to the power of minus 27 kilograms, you'll get a number of protons, which is about 10 to the power of 57 or so, right? So we don't have to worry at all. Of these 10 to the power of 57, 10 to the power of 38 is being used up by each second. So if you multiply 10 to the power of 57 by divided by 10 to the power of 38, you'll get 10 to the power of 19. So you can see that, and you convert that into years, 3 into 10 to the power of 7 seconds make a year, you will find that it will last, by this simple calculation, even older than the age of the universe. So there's no need to worry about the rate at which protons are being used up in this sort of calculation over here. Yeah, we'll use this to calculate the flux of neutrinos, okay? We'll use this to calculate the flux of neutrinos, because we saw that while 4 protons are being used up, we have released 2 neutrinos only, right? So number of protons, 4 into 10 to the power of 30 is being used up. Number of neutrinos is 2 into 10 to the power of 38. So, and you know how far away you are from the sun, which is 1 astronomical unit. That's the average distance between the sun and the earth. And you can divide this flux, neutrinos generated, by 4 pi r squared, and you would get 7 into 10 to the power of 10 per second per centimeter squared. So if you look at your little thumb and point it at the sun, that's about 1 centimeter squared. So they're about 7 into 10 to the power of 10 neutrinos going up through your little finger. They pass almost unhindered from the center of the sun. But if we can detect some of these neutrinos, then it will enable us to say whether all this is correct or not. Theoretically, it's all sound, but can we actually get some proof of it? Neutrinos are also generated, by other processes which are going on in the sun as well. But you can see that the proton-proton chain, which I talked about, generates the maximum number. These are all small fractions of it. Okay, small fractions of it, but this is the largest number. All right. When we look at the sun and nuclear reactions in stars, we may have time to look at these reactions in a bit more detail than we are doing right now. But right now, the important thing to know is that the proton-proton reaction produces neutrinos, which we need to want to detect to try and validate our solar model. So because the solar neutrino flux is actually so low, it goes through undetected, that they have devised a unit called a solar neutrino unit. So this is the capture rate per second per 10 to the power of 36 target nuclei. And from the sun, when the standard solar model was developed by John Bacon and his collaborators, it was about 7.8 solar neutrino units. That means 7.8 neutrinos would be captured per second if you had about 10 to the power of 36 target nuclei. Some of the early experiments which are done by Davis, which would lead to argon plus emission of positron, you flush out the argon, radioactive argon, you try to estimate the number of neutrinos. SAGE and GALEX were other experiments, Kamiokande, neutrino electron scattering, Cherenkov radiation, etc. Okay, but basically the message, without getting into the details of the experiments, is that what they detected was lower than what was predicted. And this was what was referred to as the solar neutrino problem. So the standard solar model predicted 7.8 and you detected 2.6. And it was not just one experiment, it was a variety of experiments. And they were all consistently lower and within the errors of measurement. So it is not that they said an error of 10, so it could be consistent. The error is only about plus minus 0.3. So there was a genuine problem with the detection of neutrinos or the standard solar model. This got resolved with the Sudbury neutrino experiment, which 1,000 tons of deuterium oxide. Okay. And what had happened was that the earlier experiment was sensitive to only the electron neutrinos. What the Sudbury neutrino experiment did was they were also sensitive to the mu neutrino and the tau neutrino. And solar oscillations, neutrino oscillations were earlier demonstrated by Takaki Kajita, for which he also got a Nobel Prize, from atmospheric neutrinos. They measured the amount of neutrinos in atmospheric air showers and showed that there could be an oscillation or change of flavor from a mu neutrino to a tau neutrino. So having got a cue that neutrinos may change flavor, the question was whether the deficit of neutrinos detected from the sun could be also due to the neutrinos changing flavor as they travel from the sun towards us. And if you had a neutrino detector which was sensitive to all the different types or flavors of neutrinos, whether one could explain the deficit.
What exactly makes them different, the different flavors?
The different flavors which are different, as we saw earlier, that they're associated with different kinds of the muons. For example, the nu mu is associated with the more massive mu meson, and the tau neutrino is associated with the more massive electron, the tau meson, the tauon. Okay, the electron neutrino, which comes from interactions with the electron. Okay, but they're all spin-up particles and they're charge 0. Now, when that was done, then the neutrino oscillations at the Sudbury neutrino experiment got a number which was completely consistent with the theoretical model, the standard solar model. So the standard solar model seems okay. And again, Art McDonald and the Sudbury neutrino and Takaki Kajita, who had demonstrated the change of flavors for the atmospheric neutrinos, they were both awarded a Nobel Prize for it. Now, besides the sun, the only other source for where neutrinos have really been detected is the Large Magellanic Cloud. And when did this happen? This happened in 1987. In 1987, there was a supernova which went off in the Large Magellanic Cloud. And this particular picture, which shows the star which went on, and it's shown by the arrow on the right-hand side, and that star exploded and releasing about 10 to the power of 53 ergs. And this is the picture on the left shows you when the supernova had taken off, after the supernova had taken off. Large Magellanic Cloud is one of our nearby galaxies, only about 160,000 light years away. And as you all know, that it got its name after Magellan, whose historian Pigafetta actually wrote down in his diaries and got attributed to him. And as we mentioned that these were actually seen by earlier Portuguese European sea voyagers as well. And of course, the Australian Aborigines were aware of the Magellanic Clouds much before the Western world had any glimpse of them. Now, as I mentioned earlier, the 10 to the power of 53 Earths is a typical energy of these core collapse supernovae, and 99% of them get carried away by neutrinos. 1% is in the kinetic energy of the explosion, and this huge light which you see, in fact, the supernova in 1054 AD, the Crab Nebula, there have been human records of seeing it by the Chinese and Indians, American Indians as well. And that carries away a tiny little fraction, about 0.01% of it. And these neutrinos are generated when this collapse takes place, that electrons combine with protons to generate neutrons. And the remnant is effectively a very condensed object called a neutron star, consisting largely of neutrons. And these electrons are, or neutrinos are, carries away the bulk of the energy. Now, this event was actually detected, recorded by three different neutrino observatories: Kamiokande in Japan, the Irwin, Michigan, Brookhaven in the US, and the Buxton telescope in the Soviet Union. And they all had consistent results, and within the errors of measurement that they could take the measurements. Within clock uncertainties, all the signals were contemporaneous. And in fact, Kamiokande was very lucky because they had taken down, they were doing some maintenance work, and it just sort of, it just happened to be on. And the supernovae and the neutrinos that come, they actually, just like they come from the center of the sun, it takes a little bit of time for the optical light to be visible. The supernovae would sort of even come before the optical light reaches you. And that is because it comes before the object becomes optically thin. Just to tell you very briefly about, I've given this an exercise for you to actually look up a little bit more about different neutrino observatories. And there is an Indian neutrino observatory which has been approved, but construction of it has run into various environmental issues, and they're addressing that. Hopefully it'll come up one of these days. So as I mentioned, that you want to minimize spurious sort of signals. So these are built underground, and they're huge detectors. The more the matter you have, there's increases the chances of interactions. And both these ones, they rely on Cherenkov radiation. The velocity of light in the medium is given by the velocity of light in C divided by the refractive index of the medium. So if you take the refractive index of either ice or water, it's in the ballpark of 1.3. So you can see light travels at about 70% of its speed in vacuum. So you can see that particles could be accelerated to velocities which are much greater than that. The neutrinos could be traveling at velocities very close to that of light in vacuum, and they could generate secondary particles, which are charged particles, which could be moving at velocities greater than the velocity of light and giving rise to Cherenkov radiation, and which these detectors will pick up. So without getting into too much of detail, I just wanted to introduce you to two of the observatories. And I mentioned about Kamiokande earlier. In fact, the Ice Cube Observatory is in the Antarctic, very close to the South Pole. And it also has an overground called Ice Top, which is used to study cosmic rays. And then they have this whole ice cube as a detector to detect cosmic ray particles, neutrinos, which can generate secondary particles. And you have these sort of digital optical modules which pick up the light signals. In fact, the website has quite a nice sort of modules or illustrations or quizzes also, trying to find out where the particle came from and what particle it could be, and what are the signatures of neutrinos. For example, here, normally you think of cosmic rays coming from above you, and that is okay because cosmic rays are not going to come through the Earth. But that is not true of neutrinos. Neutrinos can come from right through the Earth and reach you. So you can get tracks which are actually coming from down to up as well, from bottom to top in a neutrino detector. It need not be from top to bottom. It can come from any direction depending upon the source of the neutrino and source of the neutrino and the orientation of the detector relative to it. So, and that is because of the very small cross-section of interaction.